Hi, Mr. Richards here. Today's lesson is on slope and similar triangles. Our objective is to relate the slope of a line to similar triangles. Let's see what we'll learn today. If we scan the lesson and list two headings you would make to make an outline of the lesson, you may find that we'll learn about similar triangles, and the coordinate plane, as well as similar triangles, and slope. Two things to look for in today's lesson. Now, as we look at our real-world link, in an experiment using a coiled spring toy, Zoe and Jack determined they needed to raise one side of a 5-foot board 3 feet for the toy to move. Question 1. Find the slope of the board. And our hint is to use the Pythagorean theorem to find how far the end of the board is from the books. In other words, how far this distance is right here. Well, remembering our Pythagorean theorem, our right angle is right there. Our 3 we could call our A, our unknown side is our B, and across from our right angle is C, the hypotenuse, which is the 5. And our Pythagorean theorem is A squared plus B squared equals C squared. So we'll have 3 squared plus B squared equals 5 squared. 3 squared is 9, and 5 squared is 25. If we subtract 9 from both sides here, we end up with B squared equals 16. Then, if we take the square root of both sides, we're going to stay with our positive answer of B equals 4. So B is equal to 4. And now to find the slope of the board, think slope is rise over run. So we're rising 3 and running 4. So 3/4. Now as we continue on into our collaborate, we'll use this graph to discover how slope triangles are related. It says draw the triangle formed by 0, 2, 0, 4, and 3, 4. And what kind of triangle did you draw? Let's zoom in a little bit here to help us draw these triangles just a bit better. A is at 0, 2, which is right here. B is at 0, 4, which is right there. And C we're going to label at 3, 4. And so we had our A, B, and our C. What kind of triangle did we draw? Well, we could see a little bit of a right angle there with B, so this would be a right triangle. Draw the triangle formed by D at 6, 6, F at 6, 8, and G at 9, 8. Then we'll look at how is triangle DFG related to triangle ABC. Well, let's look here. We'll have 6, 6, which is right here. We'll have 6, 8, which is right here. And then 9, 8, which is out here. And this is D, F, and G. Well, how is triangle DFG related to triangle ABC? They certainly look like these are congruent. So we can write they are congruent. Now, Draw the triangle formed by 0, 2, 0, 6, and 6, 6. Okay, so 0, 2 was our A. K we're going to draw in at 0, 6 now. And D is at our 6, 6. So we'll draw this in over the top. Well, all the angles look to be the same. You can see the right angle at K and at B here, because we're relating AKD to ABC. So we have the right angle here, and this angle A is the same. And if we have two angles that are congruent in two triangles, we know that they are similar. So what is true about the hypotenuses of the three triangles in steps 1, 2, and 3? Well, our hypotenuse for triangle ABC is right there with AC. DG is the hypotenuse of that triangle. And AD is the hypotenuse of this triangle. And what we can say here, if we go down a little bit, is that they all fall on the same line. Let's see where this takes us today. Similar triangles and the coordinate plane. In the figure shown, triangle ABC and triangle BDE are slope triangles. Slope triangles are similar. So we're having angle BAC is congruent to angle DBE. So angle BAC, which is right here, is congruent to angle DBE, which is right there. Angle ACB, the right angle here, is congruent to angle BED, which is right here. And then by angle-angle similarity, triangle ABC is similar to triangle BDE. And with that, you can use the properties of similar triangles to show the ratios of the rise to the run for each right triangle are equal. And in our example, write a proportion comparing the rise to the run for each of the similar slope triangles shown above. Then find the numeric value. So we're going to compare AC to BE, which is AC to BE, those two sides compare, and set that equal to BC over DE, as the corresponding sides of the similar triangles are proportional. When we cross multiply AC times DE and BE times BC, we'll then divide out DE and BC from both sides, so that AC over BC equals BE over DE. Then, our AC was 6, our BC was 3, our BE was 4, DE was 2. They are equal to each other. So AC over BC is equal to BE over DE, or 6/3 equals 4/2. Let's see if we can do this now on our own as we go down our page. Graph triangle MNO with vertices 3, 1, 1, 0, and 3, 0, and triangle PQR with vertices 5, 2, -1, -1, and 5, -1. Let's start there before we write our proportions, and we'll zoom in here to help ourselves see this just a little bit better. So we'll have m at 3, 1, n at 1, 0, and o at 3, 0. So we have m, n, and o. And then for our triangle PQR, P is at 5, 2, which is here. We have Q at -1, -1, which is out here. And then we have R at 5, -1, which is out there. So there we have our two triangles. Next, write a proportion comparing the rise to the run for each of the similar slope triangles and find the numeric value. So let's start by writing our corresponding sides of our similar triangles. We have MO matching with PR. And again, that's our MO matching with our PR. And we can set that equal to NO over QR. So NO over QR. As again, corresponding sides of similar triangles are proportional. Now if I find the cross products here, I have MO times QR is going to equal NO times PR. And that's just cross multiplying with proportions. Now, the goal here is to get the sides in the same triangles together. So if I divide this side, the left side, by QR, so that cancels out and I can move the QR over here. This ends up canceling, and now I have the PR and QR on the same side. Likewise, if I divide both sides by the NO, then this cancels out, and my MO and NO are on the same side. So my result of all of that is that MO over NO is going to equal PR over QR. Now if I substitute in the numbers, MO was 1, NO was 2, PR, if you count, is 3, and QR, if you count, is 6. So now, what we can conclude is that MO over NO equals PR over QR, or 1/2 is equal to 3/6. And if we're just looking for the numeric value, we can just pretty much write 1/2. Remember, slope is rise over run. And so we had our MO as our rise is 1, our NO run is 2, and that relates to PR's rise, which is 3, QR's run is 6, which both simplify to 1/2. So the slopes here of these similar triangles are the same. which takes us now to similar triangles and slope. The ratio of the rise to the run of two slope triangles formed by a line is equal to the slope of the line. So as we can see in our key concept box, for the larger triangle here, our rise was 6 for a run of -3 or -2. The smaller triangle down here, a rise of 2 with a run of -1, which is also then -2. So the ratio of the rise to the run of two slope triangles formed by a line is equal to the slope of the line. The ratios now of the rise to the run of the two similar slope triangles in example 1 are the same as the slope of the line. So the ratios of rise to run are the same as the slope of the line. Since the ratios are equal, the slope m of a line is the same between any two distinct points on a non-vertical line in the coordinate plane. As we go to example 2 now, the pitch of a roof refers to the slope of the roof line. Choose 2 points on the roof and find the pitch of the roof shown. Then verify that the pitch is the same by choosing a different set of points. Well, the first set of points chosen were R and S, and so we have our formula for slope y2 minus y1 equals x2 minus x1. And so we used the points S and R, where S was our x1, y1 at 8, 6, and R was our x2, y2 at 12, 8. And you can see where this was substituted into our slope formula to get a slope of 1/2. And then we chose additional points T and U, where U this time was our x1, y1 at 2, 3, and T was our x2, y2 at 0, 2. This was substituted into the slope formula and also found a slope of 1/2. So the pitch is the same at both points, since the slope is the same. Which leads us to the stop and reflect question here on the right. Is the statement triangle RAS similar to UBT true? And explain below. Well, yes. This is true, as the two triangles are slope triangles, so they are similar. Now let's see if we can do an example like example 2 on our own, but this time with a teeter-totter. The plans for a teeter-totter are shown at the right. Using points G and L, find the slope of the teeter-totter. Then, verify that the slope is the same at a different location by choosing a different set of points. Well, let's zoom in here a little bit to get a better idea of what we're looking at. G is located at 1, 1. L is located at 7, 3. And if we want to find the slope of this, we can call our G our x1, y1, and our L x2, y2. And now remembering our formula for slope is y2 minus y1 divided by x2 minus x1. And in this question we would have 3 minus 1 over 7 minus 1, which simplifies into 2 over 6, which is 1/3. Now, verify that the slope is the same by choosing a different set of points. Well, instead of G and L, let's pick H and K. H is located at 4, 2. And K is located at 10, 4. And remembering now, our slope formula is y2 minus y1 divided by x2 minus x1. If we call this time our h our x1, y1, and our k our x2, y2, we would have 4 minus 2 over 10 minus 4, which once again is 2 over 6, which again is 1/3. So our slope at both points is 1/3. And that is it for this lesson on slope in similar triangles. Good luck.